Hello, my name is Jonatas Marques and I'll be presenting our work today. Communication networks operate with high performance expectations on latency and bandwidth, especially with the emergence and proliferation of new services and applications, such as, for example, telesurgery, VR video streaming, and algorithm trading. In this context, users demand strict guarantees, which to be met require defining clear goals for network performance, the so-called service level objectives, or SLOs. An SLO might prescribe, for example, that the end-to-end delay of telesurgery traffic has to be less than 5 milliseconds for 95% of packets, or that the bandwidth provided to a VR video streaming traffic aggregate has to be higher than 1 gigabit per second at least 99% of the time. Monitoring SLO compliance and promptly diagnosing violations is essential for the operation of today's networks. However, network monitoring is an inherently hard task, sometimes compared to searching for a needle in a haystack. That is because monitoring SLO compliance requires both detecting violations, which involves observing the network traffic with very fine granularity, that is, up to per packet analysis in some cases, and diagnosing these violations, which means pinpointing forwarding devices experiencing contentions and identifying the flows with active traffic on these devices. Existing approaches based on packet mirroring can be effective to monitor an individual flow and detect SLO violations impacting it, but diagnosing these violations would mean generating postcards on every forwarding device for every packet in the network, causing impractical overhead on control links and servers. Packet sampling helps alleviate the overhead, but inherently misses events, hurting both the accuracy and granularity of these approaches. Recent work on data center networks, such as TPP and switch pointer, attempt to strike a balance between bandwidth and processing overheads by combining analysis tasks by end hosts and in-band network telemetry, which is the collection of device metadata by production packets. These approaches are capable of both detecting and diagnosing violations in data center networks. However, control over end hosts by network operators is undesirable and even impossible in many cases, limiting their applicability. Furthermore, adapting these techniques to other types of networks is not straightforward due to the limited capabilities of forwarding devices when compared to commodity servers. In this paper, we present IntSight, a system that fully exploits the capabilities of network programmability and advances the concept of in-band network telemetry to enable the fine-grained and highly accurate detection and diagnosis of SLO violations with small network monitoring overheads and without relying on end hosts to carry out monitoring tasks. IntSight design has four main pillars. The first is the discretization of time into sub-second fixed-length slices called epochs. The second pillar is per-packet network and traffic monitoring via pathwise in-band network telemetry. The third is the per-epoch consolidation and conditional reporting of telemetry information by egress nodes. And the fourth is SLO violation detection in the data plane and diagnosis in the control plane. Next, we sketch IntSight's operation by way of an example. Consider a network with 5 devices and 5 traffic flows. The red flow represents telesurgery traffic and has an end-to-end SLO of 5 milliseconds, while the orange flow has a bursty behavior that occasionally fills up the outgoing queue in node 3 and severely delays packets of the red flow. When a red packet arrives at node 1, as the ingress node for the red flow, it updates the metadata regarding the flow in its memory and creates a telemetry header in the packet. The telemetry header contains the current epoch on the ingress node, the end-to-end delay of the packet until now, the path ID that identifies the path the packet has taken inside the network so far, the points of contention and suspicion observed by the packet, and the number of packets and bits already received for the red flow during the current epoch. Fields end-to-end delay, path ID, contention points and suspicion points are all pathwise fields, which is to say, they are updated along the path of the packet, as we will see next. When node 2 receives the packet, since it is not experiencing any contentions, it simply updates the end-to-end delay field with its hop delay and the path ID according to its forwarding decision. Next, when the packet arrives at node 3, since it is experiencing contention due to the bursts of the orange traffic, besides updating the field's end-to-end delay and path ID, it will also mark the third bit of the contention points field to signal that a contention was observed in the third hop of the packet, that is, node 3. Node 4 simply updates the end-to-end delay and path ID fields, while node 5, as the egress node for the red flow, is responsible for storing additional metadata about the flow. After updating the necessary pathwise fields, it updates the metadata to consolidate the information contained in this packet with that collected by previous packets. At the end of the 40-second epoch at node 5, since the packet just shown, as well as others, experienced high delays, node 5 generates a SLO violation report and sends it to the control plane. Control plane servers receive and analyze the generated reports to identify the culprit traffic disrupting network operation. A similar procedure is carried out for the packets of orange flow, which are marked as suspicious by node 3 because of a high packet rate. At the end of the 40-second epoch, node 5 will also generate a report to indicate that the orange flow had a suspicious behavior. In the control plane, both reports are considered alongside to identify the orange flow as a culprit of the contention and the red flow as the victim. More details on how IntSight processes packets in the data plane to compute end-to-end delays, trace paths, identify contentions and suspicions, and detect violations can be found in the paper, which also details the coordination and diagnosis by the control plane analyzer servers. Next, we present the results of our performance evaluation. One of our main concerns when monitoring a system is minimizing the overhead imposed on it. In this evaluation, we compared IntSight's resource usage to state-of-the-art monitoring and debugging approaches considering their report rate, header space usage, and device memory usage. For the comparison, we considered 6 of the most representative networks from the Repetita dataset. The smallest network, Bell Canada, has 48 nodes, while the largest, SprintLink, has 315 nodes. The number of links varies from 130 to almost 200. The total demand is in the order of 1 to 20 million packets per second. The average path length varies from 4 to about 13 hops, depending on device connectivity, while the number of flows to monitor varies from 1.2 to 50.6 million flows. To enable the comparison to IntSight, considering our problem constraints, there is no modification of endhosts, we made the following adaptations to TPP and switch pointer. We adapted TPP to extract the collected telemetry information at the end of a packet's path inside the network and send it directly to the analyzer server. Similarly, we adapted switch pointer's approach by offloading the per epoch metadata summarization task to the data plane and leaving the telemetry data analysis to the control plane. We refer to these adaptations as adaptive TPP and adaptive switch pointer, respectively. Further evaluation of IntSight, including its functional evaluation, is available in the paper. Additionally, our code is readily available along with instructions for reproducing our experiments. Next, we present the results obtained from our evaluation. In the graphs, the x-axis indicate a network topology, while the y-axis indicate the resource being evaluated. In the report rate graph for IntSight, we show the average and maximum number of reports as bars and circles, respectively, that would be generated for a violation lasting for an entire second on any single device in the network. These values are a function of the number of flows sharing each device. IntSight was able to keep the reporting rate under 1 million packets per second in the worst case for all networks, which is 1 to 2 orders of magnitude lower rate than the production traffic rate. Header space usage was kept around 25 bytes, or only 2% of the regular MTU. Finally, IntSight required about a quarter of the memory available on existing programmable targets. The difference in reporting rate between mirroring approaches and adapted TPP shows the benefits of using inbound network telemetry. This rate is reduced by up to 1 order of magnitude. Similarly, the difference in report rate between adapted TPP and adapted switch pointers shows the benefits of per-epoch reporting, which involves using part of the available device memory to store and consolidate telemetry information. Finally, the differences in utilization of all resources between adapted switch pointer and IntSight show the benefits of in-network computation of pathwise telemetry information and conditional reporting of telemetry data. Compared to state-of-the-art approaches, IntSight achieves significantly lower report rate and header usage with only modest requirements on device memory. We have presented an in-network distributed path-aware mechanism for monitoring network traffic capable of fine-grained and highly accurate detection and diagnosis of problems impacting performance, with judicious utilization of control plane bandwidth and analyzer server resources. We have designed and implemented efficient data plane procedures for gradually computing pathwise metadata such as path IDs, contention points, and end-to-end delays, and have demonstrated the benefits of pathwise inbound network telemetry compared to state-of-the-art approaches, considering 6 representative network topologies and existing programmable data plane platforms. As future work, we plan to integrate IntSight with mechanisms to solve the diagnosed SLO violations. An attractive future direction is to coordinate quick reactions that can be activated by the data plane right after an SLO violation is detected, with longer-term strategic decisions which would work in the control plane timescale. Thank you for watching our presentation.